Do you have any questions? So, thanks for your question. So this is the question I'm going to practice for today. It should be belong to 5.1, and we have a random variable t. T is the time that a manufacturing system is out of operation. So then t has a cumulative distribution function. F of t is defined for t value higher than 2. So that is guaranteed this number is positive. Well, it also guaranteed that the value when t goes to infinity is 1. Okay, so we want to find out the cost to the company is y value, that is t squared. So basically, the longer the time, the higher the cost. That's kind of my interpretation for y is the cost equal to the time squared. G is the density function for y. So we were to find the density function of y, for y higher than 4. T is higher than 2. That's why y equal to t squared. Therefore, t has to be. That's why y has to be higher than 4. That is the domain for y. And our job is to try to find the density. And you can use your own interpretation. And let's see if we do a together. And first, we will look at the function to see if it's monotone. If it's increasing or decreasing, then we can directly use the density function of the t to find the density function for y. But if it's not monotone, we should work with the CDF. Now, the t already has a CDF. This says the cumulative distribution function for t is already there. CDF, cumulative distribution function. So this is really a probability. Remember how f of t for cumulative distribution function is being defined as a probability that the random variable is less than a certain quantity. So p, so the f of t, it is equal to the probability of that the t is less than the number t. That's really the definition for the CDF. And the CDF is this. So for any probability less than a certain number, we'll be able to write it out. So that we already have it. So we can use the CDF approach. So the cumulative distribution function of y would be, we're calling it g of y. We typically use capital letter for CDF and the lowercase letter, like the lowercase g for the PDF. We're trying to find the probability density functions. We're trying to find PDF, but we can start with the CDF, and then the derivative of the CDF would be the PDF. So this is a probability definition. So the cumulative distribution is probability that y is less than the number y. The first y represents the variable y, which is equal to t squared. The second y is any random number that equal to y. So we're going to be able to calculate that probability. Now, because of the definition, according to the definition, y equal to t squared. So from here, we're able to replace a y by t squared and use that. Just want to go through the PDF approach. So this is a probability that t squared is less than y. That's because the definition for y. This is your mouse is not behaving. Right, so that's the probability we're supposed to calculate. And then we're able to convert this. T is a positive number, so we should always be able to. Right, T is a positive number, so we can write this out. We square root both sides of the equation. This is a probability that T is less than root of y. And this entire process is called a CDF approach to find the density. You start with a cumulative distribution function. Once you find it, you will find the derivative of that, which will be the density. And the question is to try to find the density for y. Now we still don't have it yet, but we do have a formula for how to calculate t less than that number, any number. This, it is equal to this. All right, so we do have a formula. So this calculation is going to equal to, this is equal to 1 minus, we follow that formula, 1 minus 2 over whatever in the distribution function. In this case, is root of y, 2 over root of y, and then square. So this is equal to, see, whatever that t is. Right now, the t is root of y. So we follow the f of t to get this probability calculated. Again, CDF, it is a probability. It is a cumulative probability, but it's a probability. So this is 1 minus, we square the numerator, which is 4, square the denominator, which is y, right? And then we're done. That is the CDF. And then all there is to find the PDF. PDF is probability density function. PDF, that would be the derivative. The only thing that we have left to do is to find the derivative to the PDF. Probably, it should be probably density function of y would be g of y equal to the derivative. And you look at all these answers, whichever one that was a derivative, that should be the correct choice. I hope that explains. This is a good example for practicing the CDF method to find the density function for any function of other variable. Y is a function of t, y equal to t squared. T squared is a function of t. So y is defined based on a formula of t. And since we have the distribution of the t, we're able to construct or compute the formula of the formula for density for y. Right. So there's one more thing to find out, which will be the derivative. This is equal to the derivative of g of y. And we already have a g of y. That would be derivative of 1 equal to 0. Derivative there is a -4. And then you're going to find derivative 1 over y. This is really 1 minus 4 times y to the -1 power. So according to power rule, you bring the negative to the front, the power -1. -1 minus 1 is -2. It's the derivative. And then you multiply -4 with 1, with -1, which is +4. That is a derivative. Any question? All right, I hope that you're able to follow through, and now we should be able to make a choice. The main thing for here is to try to figure out the routine for whenever we want to calculate density function. And the CDF is a pretty common method to identify the density function. First change the notation. All right. I think I got all 5 answers. All right. Any question from the homework? Were you able to see the homework on 5.1? Any questions? Okay, so far. So we're gonna follow what we were doing last. Well, this Monday. We were continuing on chapter 5. Okay, I think I would be using the same file. Chapter 5 will focus on having already a given distribution, and we're creating a new distribution. It could be a function of 1 variable. It could be a function of 2 variable, but these are not the determinant variable. They're random variable. So these variables, they don't follow a formula. Actually, they follow a distribution. So they're random in the sense that you can't predict what it is. The only thing we know is how do they behave statistically. 5.1 is function of 1 random variable, and there are 2 separate cases if the variable is discrete, and we will calculate the probability 1 by 1. Now, if the variable is continuous, then we'll have to look at the dependent variable to see if it's discrete or continuous. If it's discrete, then you gotta calculate the probability mass function 1 by 1 and over the summation, over the integration. So each probability should be an integration since the x itself is continuous. Now, if y is continuous, then we will calculate the density function using a calculus method. You can start with the CDF and then identify from the CDF, identify the formula for the density of for the distribution of y, and then you find the derivative from there, right? Or you can start with a density. So after we determine the formula, we realize that you already have the density for x. Find the inverse and plug in the inverse to the density function of x, and then multiply the derivative of the inverse. That will be the way to construct the density function for y. And that is when the function is monotone. Now, if function is not monotone, we may have to look at the CDF in a more detail to differentiate what from the probability part will separate part. Individually, they still follow the same formula, but from there you have to look at different cases. That's because from here to here, that conversion is based on the fact that U is monotone. U is either increasing or decreasing. If it's not monotone, we will not be able to connect these two, and that will be a problem. Right. We went through a couple of examples there, and right, we see that from a uniform distribution, you're able to construct with a function, construct a Cauchy distribution. We also have 2 results. That is, if you have if you are able to simulate a uniform distribution, you can construct a random variable for any distribution function that you prefer. The inverse is if you already have a continuous distribution, any distribution at all, you can actually construct a uniform distribution. And that is a good example whenever you wish to simulate different type of distribution. You want to simulate a Cauchy distribution, you want to simulate a normal distribution, or you can simulate exponential distribution. We can use R or any other statistical software to run out the simulation to create a data set that satisfies that distribution. Okay, this is something that we pursue. And then 5.2, we move on to function of 2 variables. You have 2 variables that you already know their distribution for, and then see this new variable y, and y1 is a function of x1 and x2. Right? It's possible to go through the CDF approach and find out the distribution of y, but we actually went by a different approach. We want to see if you already have 2 variables, they will span 2 variable coordinate system. So you can add on to like additional variable. Y2 could be just x2. Y2 could be some other variable that you created. So we can make a transformation from a set of variable, a vector x2, x1, x2 will be a two variable vector, and you transform to a two variable vector y1, y2. You transform from x1, x2 plane to the y1, y2 plane. You can consider that as a transformation. So what we're doing is transformation from this set of variable to a new set of variable. That's why we were talking about the domain. This is the domain for x1, x2. That was the domain for y1, y2. That's the first example in this section. And we do have to think about what happened. What does the transformation did to the vector itself? So this is a domain of this vector, and this is the domain for the y1, y2 vector. All right, the benefit of this perspective is it allows you to have a systematic way of solving it. If you only look at a single variable, like y equal to a function of x1, x2, and you have to go by, like you're projecting from two variable onto a one variable situation, it's lacking that symmetry. So that's why we went by a transformation approach. So you would have a transformation from x1, x2 to y1, y2, and then from that system equation, you are able to solve inverse transformation. So then from y1, y2, you can also project back to x1, x2. Once you have that inverse function, we will be able to find the derivative matrix of that inverse function. We call that J. J is an important part of the construction for the density. As you can see, if you already have the inverse, then you have a representation of x1, x2 using y1, y2. You plug in the x1, x2 that you constructed, which is a v1, v2, into the density function, the joint density of x1, x2. Now you're constructing something similar to what a density function would behave, multiply that with a Jacobian. This is a density function for y1, y2. So this makes a systematic way to calculate the density function for y1, y2. There is a little bit more detail for the reasoning in the book, but you might want to read about it. I just want to talk about the formula, the method and the formula. The essential underlying meaning of it is really a change of variable. So when you are changing the variable from kind of like this, so we're changing the variable from a x1, x2 to a set of variable y1, y2. This is something we might have done in Calc 3. When you are changing the variable, let's make the working area a little larger. All right, so for example, when you are calculating probability using the x1, x2, so probability of A, okay, it would be a double integral with x1, x2, so f of x1, x2, and then here you're going to have dx1, dx2. Right now, if you want to calculate probability with y1, y2, you have to do probability of A. I mean, for the same region, say, it will be a double integral of f of y1, y2. Here you have dy1, dy2. So theoretically, you're changing from variable, the two set of variable x1 and x2 to y1, y2. So in Calc 3, we're calling that change of variable. So how do you change the variable? What you would do, number one, is that your variable has to change from here to here. And then you have to change from this set of variable to this set of variable. That change of variable is actually J and well, I think what we did our J with this. J is equal to dx1, dy1, and dx1, dy2. And then dx1, dy1, that was x2, that's 2, 1, dx2 and dy2. It was the Jacobian matrix. This is multiplied by dy1, dy2. So this whole thing, J together, I'm gonna try to say, J together with dy1, dy2 actually equal to the dx1, dx2. Right, so the change of variable is that, so if you want to change from here to here, you have to multiply the Jacobian. So there is this, that's Jacobian. And then this part, you're going to change the variable from a representation of x to the y. So we're going to change the variable here from that part, also going to change the variable from here. It's kind of the same thing. I don't know if you remember in Calc 2, if you're changing from dx to dy, which is a rectangular coordinate, to dr d theta, which is a polar coordinate, you have to multiply at r, right? R dr d theta. That r is a Jacobian. It's the determinant of the Jacobian matrix. That is something that we can relate to, and that's kind of explain the reason we gotta multiply something extra to the density function replaced by the variable substitution. Right? Just try to explain the reasoning why the method is that way. We went through a couple of examples. The first example is here. We have a uniform distribution defined on the triangular area. The area of the triangle is half of it's a triangle for the 1 by 1 square, which is, the triangle is half of the 1 by 1 triangle, so the triangle have an area 1/2. And then that's why the value is 2, because 2 times 1/2 equals 1, uniform distribution. We constructed the division, so y1 is division between x1, x2, that's division between the two random variables, y2 equal to x2. All right, and you can determine, you can look at it, the result is y1 and y2, they're still uniform distribution. We would calculate the inverse transformation. That's the transformation from, right, this is y1, y2 formula. These are transformation from x1, x2 to y1, y2. So below we have the x1, x2, that was the inverse transformation. You can calculate x1, x2 using y1, y2. I constructed the Jacobian, which is y2. So the original density 2 has to multiply by y2 to get our density function. And that is a joint density of the two. I did work through the relation because the y2 equal to x2, and then the y1, x1 equal to y1 times y2. You plug in there, it will cancel common factor, which can end up getting the y1 between 0 and 1, y2 between 0 and 1. So that projected the domain onto a rectangular region rather than a triangular region. It causes us have different shape of the supports, which sometimes I just call the domain of the density function. All right, and then I did went through a couple. Well, Monday went through the explanation. If you find the marginal density from it, you integrate the joint density. Well, you will be able to find the marginal density for y1 and y2. You can see that there should be uniform distribution. All right, so another example is we have x1, x2, and x1, x2, they're both exponential distribution. Like that's 1/1 e to the negative x over 1. So that's exponential distribution with mean equal to 1. And suppose we have them, suppose they're independent. If they're independent, their joint density will be a simple multiplication. So you would take e to the negative x1 multiplied by e to the negative x2. That will be their joint density. And we would be able to find, and then that's something we probably have already finished talking about it on Monday. Right. So because of their independence, so alpha of x1 will equal to e to the negative x1. And alpha of x2 will equal to e to the negative x2. We have to use two separate functions because they are separate variables. They are following the same distribution, but because they are random, they actually are different numbers. So if you want to find their joint density, you have to multiply them. We're going to take this one multiplied by this one. That's why we have this. That's their joint probability density function. And then the domain would also be the same. X1 is between negative infinity, 0 to infinity. X2 is between 0 to infinity. Right, we're writing down a new variable. Y1 equals subtraction of them. Y2 equals the summation of them. Right, and this is really equal to negative x1 plus x2 if you factor out the negative. So you can see from here that is e to the negative x1 plus x2, and that would just be y2. So this is equal to e to the negative y2. But that cannot be the joint density, because in your joint density, not only do you have to have that, you also have to multiply the Jacobian. So f of y1, y2, the joint density between y1 and y2 would equal to this density substituted with the y instead of the x, multiplied by the Jacobian. So there's an absolute value of the Jacobian. We want to make it positive. So that should be the formula for the joint density. And we went through the calculation for the Jacobian. That is, you're gonna find the inverses. And when you find the inverses last time, that is, if you add these two together, you have 2 of the x1s, so you have to divide by 2. If you subtract these two, you're gonna have 2 of the x2, so you divide by 2. Right, that gives us a formula, and then finding the derivative of this matrix, cross multiply and subtract, that was 1/2. So our joint density would be 1/2 e to the negative y2. And then the domain is something that we did not finish. Right, so let's go back here. So we realized that the Jacobian will equal to 1/2. So that means the density is going to be 1/2 e to the negative y2. Now let's talk about the domain. Originally, it was the original domain was in here. It was x is 0 to infinity, y is 0 to infinity. It was the first quadrant. I hope that sounds familiar. That sounds familiar. Maybe we did talk about it on Monday. So originally the domain was everything in the first quadrant. That was original domain. That was the domain. Okay. Now this time we're gonna follow the original domain, and since we mentioned that the x1 was equal to, let's see here, x1 equal to y1 plus y2 over 2. So 0 is less than y1 plus y2 over 2. That was the x1. x1 is a summation, x2 is a subtraction divided by 2. All right, and that's that part. And then we have 0 is less than y2 minus y1 divided by 2. That was the x2. Right, because of the x2, we have this. Because of the x1 equal to this, we have this. So these are the relation. And from that relation, we realize that from this one, we must have y2 is higher than, this y2 plus y1 is higher than 0. So y2 is higher than negative y1. It's like this. y2 plus y1 is bigger than 0, so that y2 is bigger than negative y1. Right, y2 is going to be higher than negative y1. Similarly, we have the y2 minus y1. That was also positive, and therefore y2 is higher than y1. y2 is higher than y1. So that means y1 is less than y2. y1 is less than y2. That means y1 is bigger than the negative y2. I guess I should write over here. So that y1 is bigger than negative y2. Okay, I was trying to bond the y2 with y1, but turns out it's y2 bonded the y1. This is the boundary. That's the boundary. So what does it mean? On the plane, you have horizontally, that's y1, and then vertically, that was y2. On this line, y2 equal to y1. On this line, y2 equal to negative y1. So y2 is higher than y1, so y2 stay on top of this line. On this side, This is a y2 equal to negative y1. The y2 is higher than negative y1. So y2 is higher than that. Right. So our domain is in that part. So like combined effect for both equation. So it's kind of like the first quadrant turned 45 degree with the domain. That's the support. So we finish our reasoning. So basically we will have y2 is y2 is higher than y2 is higher than absolute value of y1. If that makes sense. And then y1 is between y2 and negative y2. That's why. So I'm trying to think about from both of the boundary. If you draw your boundary horizontally, you have this is a y2. This is a negative y2. So that's the boundary for y1. Draw a horizontal line, or you draw a vertical line. So this is y2 from here to positive infinity, or from here, this is this part to positive infinity. So y2 got to be higher than the absolute value of y1. That's why I'm trying to put a boundary or put a limit like into over y2. But either way, we should have in the support, we should mark out what is the natural boundary for y1 and what's the natural boundary for y2. Going back to the text, the 2 is positive. Okay. That's supports. Any question? All right, so let's give us the joint density. Again, if you want to study the behavior individually, for example, when you add up the y2, it's more like y2 and y1 that we should basically look at both of them. If you add two exponential distribution, x1 is exponential distribution, x2 is exponential distribution. If you add up two exponential distribution, what happened here? The answer is, I think we talked about this before, summation of two exponential distribution is a gamma distribution, right? One exponential distribution should represent the waiting time for one occurrence. So two exponential distribution added together, you're waiting for two occurrence, which will be the gamma distribution when alpha equal to 2 and theta equal to 1. And theta will be the exponential distribution parameter. All right. And to study that, you actually have to calculate the marginal distribution to see if it's really the density function, the marginal density of y2 should tell you it should be equal to the gamma distribution's density. And this one should also have a special distribution. But let's see. All right, we should repeat the same thing as we were mentioning before. Whenever you look at a distribution, you should have the density. If it's continuous, you should have the density, you should have the mean, you should have the variance, you should also have the moment transient function. So if you want to study something extensively, you should have all four. Obviously, we might not have sufficient time for like y2 and y1. We probably can't study both of them. At least we should figure out their density. Let's go through a couple of common things. For example, if you already have their joint density and you want to calculate the probability for a continuous case will be an integration. So it will be, let's say we want to calculate probability y1 larger than 0, y2 less than 4. What do we do? We'll be integrating the joint density because in this probability calculation, there's y1, there's y2, and you're gonna have to include both. For y1 larger than 0, so y1 will be integrated from 0 to 4. It's not as simple, right? So let's see how we like. Remember with two-dimensional case, we may have to look at the integration domain. Let's see how we do it. Let's see how much it's on the integration area. Maybe a little bit too hasty. We know it's talking about. Right, for example, if we were calculating this property, right, how do we calculate it? The original one was this. This is y1, and this is y2, and this is our original integration region. Okay, we want to calculate probability that y1 is larger than 0, which is everything this part. I mean, originally it was like 2, but now we want y1 to be positive, right? y1 to be positive. y2, you want it to be less than 4. Okay, so this is a y2, and you want to find the value 4. Okay, 4. Okay, so our integration region is over here. So is that little right triangle, right triangle? And that's kind of explain why this integration region are like that. You can do dy2, dy1, and you can do dy1, dy2 with your hands. That's why there are two different formula. If you want to do dy2, dy1, you need numerical boundary for y1. And then the y1 is going from, this is the y1 equal y2, so that must be the same thing as 4. So your y1 is a numerical boundary that goes from 0 to 4. And then the y2 is this. y2 would be a variable boundary. The upper boundary would be the 4. And the lower boundary is right here. And that is on the line y2 will equal to y1. So your y2 will have a lower boundary that equal to y1, right? That's how this integration is. The other way is to do it opposite. You want to have the y2 to have numerical boundary. Now the numerical boundary for y2 would be this and this. So numerical boundary for y2 is 0 to 4, and then you will have variable boundary for y1, and that is you're going to look at. Try to find some color. So let's see this one. All right. So the y1 would go from here to here. So the lower boundary for y1 is 0, and the upper boundary is on that line. That line is when y2 equal to y1. So then y1 equal to y2. That y2 will be the upper boundary. So that kind of explains why do we have two different formula for computation. We didn't finish the computation, but it shouldn't be too hard. I would say I would go by this one because it's easier to get a number out of it. So you integrate 1/2 times e to the negative y2 over -1. You will evaluate at 4 and evaluate at the y1, and your answer will be an exponential function of y1, and you integrate 0 to 4 dy1. I think the first one would be slightly easier to integrate. If you go by the second one, I guess that would be okay. The inner function, the integration function has no y1. So when you add dy1, these are all number you can bring out. So that will be integrating as y2 minus 0. But then your y2 is multiplied by e to the negative y2. You have to, in the outer integration, will be a little bit hard because you have to do integration by part. So calculation-wise, I prefer this way. We go ahead, calculate integration. The second part is a little, well, if you are okay with integration by part, I guess that would be okay. So this method is slightly better than the other one. So we're going to skip the computation part, but you can try practice the calculation. The answer should be in the book. Okay, so this is the calculation part. You can see if you do integrate, if you do use the second one, and solution actually is in here. So if you are doing this one, this is a solution, this calculation part. So when you finish the inner integral, the outer integration have this, and that's why you have to do integration by part. So this computation is not direct. This is the final answer you get. I would definitely prefer this one. Is computation is slightly easier. Since we have that, maybe we should. This is already here. So let's see the computation using this approach. All right, it should be the same answer though. So you go 0 to 4, and then we're going to integrate this function. It's going to be the antiderivative is 1/2 e to the negative y2 over -1. Because we're dy2, y2 is a variable. You're going to plug in 4 and plug in y1. and then dy1 is a next step. If you plug in the number for the 4 for the y2, so you have negative 1/2 e to the negative 4. That's when you plug in the 4. If you plug in y1 minus negative, make it positive. So that is going to be 1/2 e to the negative y1. So that's what we have. And then we're going to integrate dy1 after we finish that. And 0 to 4. This is equal to. We'll integrate the 1/2 e to the negative y1, which is e to the negative y1 over negative 1. And then if you integrate this one, it's a number, so the antiderivative will be e to the negative 4 times y1. And then we're going to plug in 4 and plug in 0. I still need more space. So the calculation is so equal to, we plug in 4, it will be negative 1/2 e to the negative 4 minus 1/2 4 times e to the negative 4. So when you plug in the 4, if you plug in 0, this will become 0. Now this one is not 0. E to the 0 equal to 1. So that would be plus 1/2 if you plug in 0 to 4. And we have this. Altogether, it would be the same value out there. But I think the computation should be shorter, because in here we have this result for the antiderivative, but the antiderivative needs this one needs a lot of extra steps. So I think the first integration should be easier. We should try it, but it's the same answer. All right, this is that one, and let's talk about marginal distribution. The joint density tells us together y2 and y1, how do they behave? But if you want to figure out what was the distribution for y2, what was the distribution for y1 individually, you have to do the marginal distribution, right? To calculate marginal distribution, we'll integrate one of the variables to make sure the function only have one variable left. So this is a calculation for the marginal distribution for y2. So you're going to take the joint density one. Let's try to think about the reasoning why it looked like this. All right. This is trying to calculate the marginal density for y2. Right. Originally, the joint density was f of y1, y2. It equal to 1. I believe it was 1. Well, this one is equal to 1/2 e to the negative y2. That was the joint density. So if you want to find the marginal density, we're calling it G2 because it's for y2. So G2 of y2 is defined by its integration of the joint density. But you want to get rid of one of the variables. Since we're talking about variable y2, we want to get rid of y1. So you have to do dy1. Try to explain why that. And then you want to find out the natural boundary for y1. And remember, that was the integration boundary. All right. So what was the boundary for y1? This way. So the boundary, this is negative y2, this is positive y2. So if you want to find out inside the integration, the natural domain in the density function, it's going to be negative y2 and then positive y2. That was the boundary for y1. So then the integration limit looks a little bit weird. That's because the domain of the density function. So we were supposed to integrate dy1. Right, the function itself has no y1. So integration-wise, you bring that outside. That is the same as that density function. You bring that outside of your integration. You go negative. You go 1/2 e to the negative y2, and now you have integration y2 negative y2 dy1. It's the integration of 1. So if you integration by 1, then the antiderivative will be y1, plug in y2 or negative y2 for y1. And that this entire integration is 2 times y2. So y2 minus negative y2, so it's 2 times y2. So you got 1/2 e to the negative y2 times 2y2. And cancel one of the y2. And that's why the final result for the density is y2 times e to the negative y2. That looks exactly what it should be in a gamma distribution, right? So that is a gamma distribution when the alpha equal to 2. Right? You kind of remember the gamma distribution, it was, I put it over here. Gamma distribution, the density function look like a 1 over gamma. That's kind of the reason it's called a gamma distribution, because we have gamma as a coefficient. 1 over gamma, theta to the alpha, x to the alpha minus 1, e to the x over theta. In our example, theta equal to 1, so these are all equal to 1. Don't worry about the theta. That equal to 1, that equal to 1. And at alpha, since we have y equal to x to the alpha minus 1, we don't have x, we have y. Y to the alpha minus 1, so that 1 is alpha minus 1, so therefore alpha should be 2, right? So it's a gamma distribution with parameter alpha equal to 2 and theta equal to 1. That's the connection, that's the distribution. We give them names. Alpha is called the shape parameter in the gamma distribution. Then theta is called the scale parameter. So scale equal to 1 and shape equal to 2. It's the, you can write it out. Any question? In R, we actually have the function. That's why I'm trying to name it. Because R has a function that's called a distribution. They calculate any distribution for you. You do have to identify the alpha, so like shape equal to 5. You also have to identify something called a rate. The rate is actually the lambda, so lambda equal to 1 in our case. So it calculated for you. I mean, maybe that doesn't really make much difference, but it calculates the density value for you. You ever want to graph it or calculate it? Right, just want to remind that we can identify the distribution of the function by the appearance of the density. So the density function and the density formula have a 1-to-1 match. And that is the distribution for y2. Since we already knew the distribution, we know the mean. The mean for a gamma distribution is alpha times theta. In this case, theta equal to 1. So then the mean for y2, the mean equal to 2. And then the variance equal to alpha theta squared, which also equal to 2 in this case. All right, another one is y1. Remember how y1 was defined, right? Y2 is a summation. If you add a 2 exponential to x1, x2 exponential distribution. If you add a 2 exponential distribution, you have a gamma distribution. Now here, this is something new. If you are subtracting 1 exponential distribution minus another distribution, another random variable, 2 exponential distributions subtracted, that's y1. We might want to know how y1 is behaving and what's the density function for y1. We're going to do the same. We were supposed to integrate the density function, but then the density function has to be integrated over y2. But y2 it has different boundary. That's why we end up having 2 integration. So the original boundary for it, this is what it is. So this is y1 and this is y2, right? So if you want to find what was the integration boundary for y2, you will see that if y1 is, we're trying to find the marginal distribution for y1. If y1 is negative, okay, what happened to y2? Y2 goes to from negative y1 to infinity. That's when y1 is negative. Now, if y1 is positive, and then what happened to y2? Your y2 is go from here to infinity. Remember, this is the integration. This is the integration region. So it's from here to here. So that will be a y2 to infinity, it was integration limit. So we actually are integrating the density function dy2 because we want to get rid of y2. We want to have a formula for the marginal density of y1, and therefore dy2, the integration process, get rid of one of the variable. And then when you do this, the antiderivative of e negative y2 is e negative y2 over negative 1, and then we plug in the y1, which is what we have. The upper limit at infinity, e to the negative y2 when y2 approaches infinity is 0. So it's the only thing we have. And this is the same way. You plug in the negative y1 into the negative y2. It's going to be e to the positive y1. Right? And turns out we just want to have a density function that actually makes sense, since y1, the actual boundary for y1 can be negative or positive. So we want e to the negative y1 absolute value, e to the negative absolute value of y1, and that will guarantee that the function itself is like positive and below a certain boundary. You don't want it to explode. So you cannot have e to the y1 when the y1 is positive, because if y1 is positive, e to the negative 1 is really, really large. And density function have to have an area equal to 1 below the density function. So y1 e to the negative large number is fine, e to the positive large number is not fine. And that kind of explains why we have a negative there when it's positive, but we have a positive there when we have negative y1. Right, so this is a, it looks like an exponential distribution, right? The natural exponential distribution will be e to the negative y1, but now we have both sides of it, and therefore we have to cut it in half, so that way the entire area below the curve will equal to 1. And this is called a double exponential distribution. The actual exponential distribution only occupy the positive part of the plane. I mean, if you are thinking about y equal to e to the negative y, negative x, right? It's this, that's how we behave. Now we have y equal to 1/2 e to the negative x. Just want to make absolute value of x. All right. What it does is, if you only have this part, it gets this area equal to 1, the area below the curve. So we kind of have to lower it to, this is 1/2. Right. So the area below it together with the area on the other side, the total area below the curve will equal to 1. Right. So if you keep it equal to 1, understandable. If you do not have the 1/2, the area below the entire thing is going to equal to 2, which is not good for density. And that 1/2 kind of makes sense to have it there. That's the double exponential distribution. It actually has certain symmetry to it. Originally, the exponential distribution is right-skewed. It's not symmetrical. But the subtraction of two exponential distribution actually is symmetrical, because x1 and x2, they're both random. So it could be sometime that the x2 is larger, sometimes x1 is larger. So then it causes a y1, which is a subtraction. The y1 can be positive or negative. Where was it? I think I went past it. Right. So x1, x2 are exponential. The subtraction of them can be positive or negative. So y1 can be positive or negative. On the other side, x1 and x2, they're both exponential distribution. So x1 and x2 are both positive, and that is the reason why y2 is guaranteed to be positive. So y2, it is a positive variable, but y1 could be a positive or negative variable. y1 has symmetry on the density function, but y2 does not. So gamma distribution, which is also right-skewed. So some of the property is understandable algebraically. Some of them you might have to look at its own density function. Any question? It's another special distribution. We sometimes call it the Laplace probability density function. All right, so let's look at another one. This is called, so earlier we had two exponential distribution. We added together, which end up being a gamma distribution. Now let's look at two gamma distribution. If you combine two gamma distribution, what will happen? And chances are, if you're adding it, this is something we talked about before. If you add two gamma distribution, the result will be another gamma distribution. The thing that is new in this case is y1. We define it as a ratio x1 divided by the summation of x1 plus x2. And I think the result will be less than 1 because your numerator, it is obviously smaller than the denominator. So this is the definition for y1. We can see that should be something less than 1. And also x1, x2, they're both gamma distribution. Gamma distribution are always positive. So understandable, y2 is a summation of two positive number. Therefore, y2 is positive. y1 is a ratio between two positive number. Of course, y1 is also positive. So we can see the natural boundary that y1 would be a number between 0 and 1. I hope that kind of makes sense. So we kind of see before we even do any calculation, we know y2 occupy the whole upper part of the plane. And y1 will only occupy the value between 0 and 1. Okay, so let's look at how they behave. Suppose x1 and x2, they're independent gamma distribution. The shape parameter is different. The x1 has parameter alpha, x2 has parameter theta. They have the same scale factor, they're both equal to theta. Right, that's why you can add it together. When you add it together, they will still have theta as their scale factor, scale parameter. Their shape will be alpha plus beta. So that's y2. Y2 is a summation. We kind of see what's going to behave. But let's look at the division. All right, the joint distribution. If they are dependent, their joint distribution will be a multiplication. So we're multiplying two gamma distribution. It helps to have that review already in here. That's the gamma distribution. A gamma density function have a gamma alpha. The gamma alpha, it's a multiplication of the exponential distribution of the variable and the power function of the variable x. X to the alpha minus 1 power, e to the negative x over theta. That's the exponential part. So all gamma distribution have these two parts, and then we'll multiply them. Right, so you would have e to the negative x1 over theta, you'll have e to the negative x2 over theta, they are multiplied, that's why the exponent is being added. And then we have x1 to the alpha minus 1 because x1 has parameter alpha, x2 has parameter beta, so we have x2 beta minus 1. Those are the parts that belong to that density. We have gamma alpha, gamma beta in the denominator because the density is supposed to have the gamma factor in the denominator, and then we have theta to the alpha and theta to the beta, and then before we add alpha and beta. So together, this is the joint density of x1, x2. Now we want to know what the joint density between y1 and y2. Now y1 is a ratio, y2 is a summation between the two variables, and we're going to know what was the joint density. The process is similar. We are going to reuse this density. We're going to plug in many numbers. For example, these are all numbers, gamma alpha, gamma beta, theta to the alpha plus 1. They are just numbers, so they're just going to be the coefficient. And we were supposed to replace this. All right, x1 plus y2, x1 plus x2 is the y2. So that's just y2, e to the negative y2 over theta, right there. That can be directly substituted. Now over here, the x1 times x2, we have to find a way to rewrite it. And that's the part that needs a little bit of work. And for us to do that, we have to find the inverse transformation. You have to find what is the representation for x1, x2 using those. All right, so I guess we can do this. All right, so we're going to try to see the process and then understand what's being written in there. All right, so let's try to find the inverse. If you look at this transformation, so this is a transformation from x1, x2 to y1, y2. We want to be able to solve x1, x2 from this. One thing is for sure, x1, x2 summation equal to y2. So bring that into the first equation. You're going to see that the y1 is equal to x1 over y2. Right, let's simplify that a little. And then from that, you can multiply both side equation by the denominator. We have x1 is equal to y1 times y2. Y2, and then you're going to bring that to the x1, where that x1 is. And then we have the x2. X2 is equal to y2 minus x1. That's from this equation. And then since the x1 equal to a multiplication, so it's y2 minus y1 times y2. So x2 can be represented. Now we have an inverse, right? We have a representation for x1. We have a representation for x2. This you can also factor out the y2 to see this is actually y2 times 1 minus y1. I don't know if that helps, but write it out. Right, so now we have, you keep this part in your final joint density. You're also going to replace that by y1, y2 to the y1, y2 to the alpha minus 1 power. You replace that one by y2 times 1 minus y1 minus y1 to the power of beta minus 1. And this is going to be e to the negative y2 over theta. And together with everything, gamma alpha, gamma beta, and also all that coefficient. And then other than that, we have to multiply a Jacobian to try to find out the Jacobian matrix from there. Any questions so far? We're almost finished, except the last part, which is the Jacobian. Now, this is an explanation I did. So this is the inverse, and then we find the Jacobian. That is, you find the derivative of x1 with respect to y2, y1. You find the derivative of x2 with respect to y2 and y1. You cross multiply and subtract y2. A couple of terms are simplified, so the Jacobian actually equal to y2. So now we back to here. Substitute x1, substitute x2, and then there's e to the negative y2 over theta. And there's the absolute value of y2. That's the Jacobian, absolute value of the Jacobian. The y2 is positive anyway, so we don't have to have that absolute value. So, any question? No, we already have the joint density. Another thing is to look at the domain and know, like we already kind of know the domain. Y1 is between 0 and 1. Y2 is between 0 to infinity. All right. Now we want to find the marginal density. So one of the things that we already knew, we knew kind of what was the behavior of y2. But if you want to find the marginal density for y2, you will see that it is a gamma distribution. And this one, the one we mostly concerned is what's the behavior for y1. So we're going to find the marginal density for y1. And that's how it looks like. You can do the integration yourself, which is integrating this function dy. We want to find the distribution for y1. So we're going to do dy2. We're going to have a dy2 here. So when you do that, you are going to keep every term that has y2 and then get rid of the one that has y1. That's what we have here. So bring anything that related to y1 outside the integration, because those are multiplications. And we only keep the part that's related to y2. We want to find the marginal distribution for y1, so y2 has to be integrated. And then we already have a gamma alpha, gamma beta coefficient that was also unrelated to the integration variable that was here, right? This part is a gamma function. So this part equal to gamma alpha plus beta. So this function become gamma alpha plus beta over gamma alpha, gamma beta. And then we have y1 to the alpha minus 1 and 1 minus 1 to the beta minus 1. This actually are part of the formula already. You see the alpha y1 to the alpha minus 1 and then y2 to the beta minus 1, which was already in the density. Everything else was integrated out. We end up having this. This density function have a special name. It's called the beta function, beta density function, beta distribution. The reason why it's called a beta distribution is because the beta function, the beta distribution, beta beta distribution and beta function actually are not the same thing. I want to mention what is a beta function exactly. Beta function is beta alpha beta equal to beta function is defined on top of the gamma function, is defined by gamma function equal to gamma alpha gamma beta divided by gamma alpha plus beta. Right, that's the beta function, and that's why this is called a beta distribution, because it has a beta function as a coefficient. This is actually a coefficient. You can also write this coefficient, this number, as a beta number. It's actually equal to the 1 over beta, alpha beta. That's why it's called a beta function. What's interesting about this is that for a beta function, the variable is between 0 and 1. That made it a really nice model for probability. So if you want to know how you want to find a function, I kind of explained the behavior of probability value. And the beta function's definition is self-guaranteed that it's between 0 and 1. Another thing is beta function by definition is this. Beta is defined between 0 and 1, like y to the alpha minus 1, and then 1 minus y to the beta minus 1 dy, and that's the beta alpha beta alpha beta. All right, that is if you are trying to integrate this, it's equal to b there. But since we have a denominator of this, that guarantees that if you're integrating this function from 0 to 1, integration of this density equal to 1. If it's integrated from 0 to 1. That kind of satisfies the definition for the independence function. The integration of the density function on this domain should equal to 1. So the denominator, this combined has 1 over the b alpha beta. If you integrate this one from 0 to 1, that's also b alpha beta. That's kind of explain the reason why this distribution is called a beta density. Yeah. This is how it is before it's integrated. We don't integrate it. Density function you don't integrate. If you integrate it, the entire thing will equal to 1, and that's how beta is defined. And we can prove that this beta number equals the division of those gamma number. Right, a couple of background information on this. So it's a special distribution. So we kind of see that if you are defining the a ratio, a numerator is a common distribution, denominator is summation of two common distributions. This ratio, which is a number between 0 and 1, this ratio can be modeled by a beta distribution. That's something to take away from this results. So you can see that we've been studying the joint distribution for 2 different variables, but then once you go ahead and find the marginal distribution, it explains more of the individual behavior of those variable y. All right. So let's try to define one more thing that is popular in the later half of the book, that was statistics. All right, so what if you have a variable defined by the division of 2 chi-square distribution? Suppose U is a chi-square distribution with degree freedom R1. V is another chi-square distribution with degree freedom R2. So W equal to U over R1 divided by V over R2, right? And we want to know the distribution of W. I know the results. W have a distribution that is special. It's called the F distribution, but we still want to know what was the density function looks like. So we're going to try to go by the CDF approach. We're going to use the CDF approach. In this case, we did not create another variable to go with it. We just want to find exactly what is that distribution. So basically, if you have a function of 2 variables, well, we got 2 variables, U and V, and you want to know what's the distribution of it, you can do 2 things. Number 1, you can do what we did earlier. That is one thing, another thing, you add something else to it. It could just be y2 equal to x1, and you just made a system. So now from x1, x2, we're transformed to y1, y2, and we're able to construct the joint distribution. From the joint distribution, we can go ahead and find marginal distribution and the marginal distribution of the individual variable tell you the distribution of your new variable. Right now, or we don't do all that. We don't deal with the matrix. We don't deal with the two variable. We will just look at the using the CDF approach to study the behavior of that variable. It's still not that simple because we are looking at a distribution of probability related to U and V. You still have to have a joint distribution between U and V. So here is what do we do? So we're gonna suppose W equal to that division. So the CDF approach will be what is the probability? The CDF for W will be FW, which is a distribution for variable W. That is the W variable is less than the lowercase w, or the U over R over V over R is less than W, right? And we multiply both sides of the equation with the denominator, which end up getting us this. All right, now we need to know how to calculate that probability. Calculation of a probability related to two separate variables require us to know the distribution for U and V, or the joint distribution for U and V. So now to go forward from here, we need to know what does U and V's joint distribution is. This is going to be, since we involve two variables, this probability calculation will be a double integral on that integration region. This integration region will be marked out by the boundary. U equal to this is the boundary of the integration. We integrate over the half of the integration plane. So anyway, it needs us to know the joint density between U and V. So now we're writing the joint density of U and V. U is chi-square. So this is a chi-square distribution. Remember, chi-square distribution is a special gamma distribution. So we have gamma alpha equal to R over 2, and then theta equal to 2. So that's our theta. And this is, remember, chi-square distribution and gamma distribution, they are both multiplication of the power function and exponential distribution. So we have e to the variable over the theta equal to 2. And here we have alpha, the variable to the alpha minus 1. And alpha is R1 over 2. And this is the same thing, just we replace R by R1 by R2. And then multiplication of them will be the joint density. So that looks at exactly how we multiply two chi-square distribution. All right, multiply those to give out the joint density. So integration of that one, we were supposed to integrate the joint density over the integration region. Now, what was the integration region? Original integration region is U is from a positive number, V is a positive number. So U and V are both positive. When both variables are positive, it's in the first quadrant. We're integrating in the first quadrant. But now this U equal to R1 over R2 times the W is a positive number. Time of W times V, that is a slope time of variable V. This is a line. U equal to R1 over R2 W times V. That is a line. Since U has to be less than the V, so that is integrating the U variable. That will be the upper boundary for the U. So you're integrating U from 0 to that, and the natural boundary for V will be 0 to infinity. That's our integration limit. So we'll go ahead and integrate it. The process is kind of long. We have to do it step by step. See if we got time. Well, we're over time. I recommend you guys try to look at the calculation of it. There's calculus involved in the process. It's a pretty long, lengthy process for interpreting it. We're not supposed to memorize the F distribution, but it's interesting to know how it's being developed. We see F later in other statistical test procedure. So now we kind of see the source of it. Like, what was it originally? How is it analytically defined in the integration? All right, we'll come back to it later. That's it for today. Thank you. Please read this section. I feel like it's stuck into it pretty long. Very serious theoretical. I'll see you next time. Thank you.
I signed up for the test.
Which day?
It's going to be on Monday, right after this class.
Okay.
Yeah.
Okay.
12:30.
12:30. Thank you.
Okay.